Very warm good evening to all of you. Uh, Welcome to day 5 of AICTE Atal FDP program on AI empowered electric vehicles in smart grid systems, challenges and opportunities. I am very glad today we have a renowned expert, Dr. Vidyasagar sir, from uh, a senior power system engineer from Blake Clough Consulting, United Kingdom. On behalf of Department of Triple E, Sri Vishnu Engineering College for Women, we wholeheartedly welcome Dr. Vidyasagar. So thank you, sir, for joining today. Welcome you, sir. And thank you for being part of this workshop and accepting our invitation. And I take this opportunity to welcome all the participants who have joined here. Now, before proceeding over to the session, let me ask Dr. M.B. Srikanth to introduce today's speaker, Dr. Vidyasagar. So please request Dr. M.B. Srikanth to introduce the today's resource person.
Thank you, Dr. Dilip. Good evening, all the participants. Good evening, Dr. Vidyasagar. It is my pleasure to introduce Dr. Vidyasagar Ellapu. Completed his graduation in Electrical and Electronics Engineering in 2007 and PG in College of Engineering JNTU Anantapur with specialization in electrical power systems. He obtained his PhD from Homi Bhabha National Institute, Mumbai in 2016 for his works on fault detection and isolation of neutronic sensors of nuclear reactors in Bhabha Atomic Research Center, Mumbai. Dr. Vidyasagar has a teaching experience of around 4 years in Electrical and Electronics Engineering Department and a postdoctoral research experience of around 3.5 years. He conducted postdoctoral research works in Shanghai Jiaotong University, China, and University of Huddersfield, UK, where he worked on health assessment of retired EV batteries for the second life applications. He published research papers in prestigious journals, including IEEE Transactions on Nuclear Science and many international conferences. He is currently working as a senior power system consultant in UK. Thank you, Dr. Vidyasagar. Thank you for accepting the invitation. I request you to start the session.
Hey, good evening, everyone. It's my pleasure being in this FTP. Today, I'm here to discuss some concepts around curtailment and the role of electric vehicles in the curtailment. Let us go into the details of this discussion. Yeah, first of all, let us understand what curtailment is. A curtailment refers to a reduction of electricity generation from renewable sources such as wind, solar, due to grid constraints, oversupply, or lack of demand, preventing full utilization of available renewable energy. Means uh, there are some energy sources, renewable energy sources that are situated in the entire geographical area, and those are connected to the networks as well. But there are some constraints in the grid, and at the same time, there is some excess generation because of maybe because of some excess wind. The generation will be higher. At the same time, if the demand is not that much, there is a imbalance between the generation and demand. So in order for it not to cause any instability for the network, there should be a reduction in the generation. That is what is called curtailment. That curtailment can be maybe because of these grid constraints or inadequate capacity with some grid assets, or maybe due to the stability constraints. So, in order to discuss further, we need to understand relevant concepts such as net zero targets of different countries, various countries, existing networks, and the challenges associated with the networks, curtailment, and relevant aspects, different network management schemes, and ANM. ANM is Active Network Management Scheme, and the role electric vehicles plays in the concept of this curtailment. We will see all these concepts one by one. Let us first go to the net zero targets. What is net zero? Net zero refers to balancing the amount of greenhouse gases emitted with an equivalent amount removed from the atmosphere, achieving a net zero carbon footprint. So whatever is emitted is absorbed. That is what is the concept of net zero. Uh, let us look at the countries with the highest carbon footprint. Here, 10 countries are listed from 1 to 10. China being the top in this list, South Korea being the least in this list of 10 out of 197 countries, and India is also there, occupying position 3. China has a percentage of CO2 emission of around 33%. US has that 12.6%. India has around 7%, and the list goes on. 1.53 for South Korea. There are many other countries in the world with this carbon footprint. Uh, we know that there is increased awareness on this net zero or carbon footprints. So countries have set up some targets to reach net zero. So here are the targets for various countries. The target years are ranging from 2050, and means there is no what is called a distinct target date. The target dates are varying. Some countries have a target year of 2045, means they have set up this target year such that they reach 20 by 2045 they reach net zero. Some have a target year of 2050, some have 2065, some have 2070, and we can see that some countries don't have any target set up yet. For achieving the net zero or balancing the net zero is practiced by all these countries have to follow these steps to reach net zero. The first one is reducing emissions. Whatever the current fossil fuel emissions are there are to be reduced. Maybe because of that can be reduced by replacing the existing generation with renewable energy, using highly efficient energy resources, and employing low carbon technologies. By using these carbon removal technologies, we can reach net zero. Means it is capturing CO2 via natural methods or technological methods like carbon capture and storage methods. After doing these two things, we can offset by investing in carbon credits or offset projects such as reforestation or and renewable energy. Uh, and not only the policy makers such as various countries set up net zero targets with the involvement of various stakeholders such as DNOs or any network operator, industries or individual customers. All these stakeholders can participate in this in the goal of reaching net zero. So all these stakeholders can follow some different pathways to achieve net zeros, which are represented by future energy scenarios. It is future energy scenarios explore pathways to achieve net zero, balancing energy demand and supply while reducing carbon emissions. These scenarios typically include high renewable penetration, means uh, the renewable sources can be installed wherever it is possible. Expansion of wind, solar, and hydro energy can be done. Electrification, increased use of electricity in transport. Nowadays, transport is majorly through fossil fuel resources instead of the fossil fuel based transportation. If we use electricity in transport sector with the use of EVs, electric vehicles, we can accelerate the journey to our net zero. Heating in the countries such as in the countries with the reduced with low temperatures, they use a lot of heating in winter season. So if that heating is electrified, then we can accelerate the journey to net zero, and industries can adopt this electrification as well instead of fossil fuels. Grid flexibility and storage, advanced battery storage, demand side response, and smart grids. These can be employed. That means if there is an excess generation, instead of curtailing the generation or reducing the generation output from each of the generators, we can send that excess generation to a battery storage that uh, that forms this grid flexibility. Demand side response. Demand side response. If there is mm, not enough generation, then the network operator sends some signal to the demand so that the customers reduce their electricity usage. That is demand side response. If there is excess generation at some points of time, then they use the electricity at that time instead of not overloading the existing assets. That is what is demand side response. Smart grids is establishing communication between the network operator and the customers. Hydrogen and carbon capture, low carbon hydrogen and carbon capture utilization, storage to decarbonize hard to abate sectors. Energy efficiency and digitalization can also be used to accelerate the journey to net zero. We can see that most of these discussion is concentrated so far on uh, the renewable energy penetration. With the use of this wind, solar, and hydro energy wherever it is possible, right? So that is the key concept involved in reaching net zero. However, is the existing network ready to have this increased penetration of renewable sources? That is the important challenge we have.
Hello, can you make it to the full screen?
Full screen, okay. Means you mean slideshow? So yeah.
Yeah, the existing network challenges, the figure is not actually clear. Can you make it bigger?
Oh, this one.
Yeah,
This figure you mean?
yeah.
Yeah, this is just for representation purpose only. It doesn't carry much information, so uh, I think it doesn't. Uh, you mean this one, right? So it is just for representation purpose only. So even though it is expanded, there is no much information that can be conveyed to you. So what I want to tell is that this is a typical GB transmission network. You can see these voltage levels, right? 400 kV, 275 kV, 220 kV, 132 kV. And this is a part of the GB network or Great Britain network. Though the concepts are expressed in terms of the GB network, those are generalized concepts, and those can be adapted to any country as well. So I'm explaining the concepts in the context of GB. So I hope that is fine. So my idea here is to represent the network. It is highly measured, right? Here are some substations. The generation is situated away from the customers, and the customers are somewhere. in order to supply power to the customers, there should be some transmission network. This is the transmission network. It is highly meshed. The if it is found that there is some generation here, then that can be connected to this transmission network. But these circuits may be of full capacity. That is what is the concept of this curtailment, and that is the biggest one of the biggest challenges faced by the curtailment. This in the next slide we will see. In the next slide we see the uh, second part of this figure. Second part of this figure, this is the same. It has many substations here and many lines at various voltage levels. The key assets are transmission lines, substations, transformers, circuit breakers and switchgear, reactive power devices, control and protection systems, fax devices, HVDC systems, and so on. All these are the key assets of the network, and they may mm, there may be some constraints to the generation or renewable energy integration. That is the concept behind this. And coming to, if we go further in voltage levels, so far we have seen the network till 400 kV to 275 kV. And if we go further, we reach the distribution network. This is a typical distribution network uh, having all the voltage levels from right from 132 kV. Here is 132 kV. This is 33 kV network, and this is 11 kV network. We can see some underground cables here, some overhead lines here. All this forms the distribution network. If we go a bit further, this is the 33 kV substation. We can see the bus bars here, and these are the transformers or grid transformers. They step down from the 132 kV to 33 kV, and these are transformers associated with primary, the various primaries. This is one of the primaries. We have three transformers here, which are 33 kV by 11 transformers. And if we go further, this is the network of that particular primary. It has a long bus bar, and it has, yeah, this is the bus bar, and it has many feeders connected to it. It is looking like a mesh network again, but even though it is looking like a mesh network, it is not mesh network. There are some open points, normally NOP. Those are called normally open points. So those are normally open, and uh, in the case of a fault here, then this particular portion is isolated from rest of the network, and the remaining parts of this circuit are given power to the neighboring feeders. So this is a open loop configuration of these radial feeders. Yeah, in this structure of this network, let us look at a primary, and suppose we are connecting a new load here at this point. So this particular feeder already has some loading, forecasted load demand. On the top of that, there are some acceptances are recently energized, energized demands. So they superimpose on this forecasted loading, and on the top of that we are adding a new load, so its current, its power is also gets added to this particular line. That means this line has to carry all this load demand. In this case, if there is a fault here, the major concern for any network operator is to give continuity of supply. So in that case, this particular portion has to be immediately isolated from the rest of the network. One, two, three, four, all these open points, all these closed points are made open. Then this particular section of the network is isolated, and rest of the network is to be given supply. In that case, because of this new load, some of the sections of the networks may get overloaded, and those sections are to be reinforced. That is the approach followed by the DNOs. But that is not true for the case of a generator. A generator has to adjust with the network it was given. For the case of demand connections, the network can be reinforced. And for the case of generation connections, security of supply is not that much important. So it has to adjust with the existing network. That is the challenge faced by the generation connections, because reinforcement is associated with a lot of public disruption that is not welcoming. This is the overloading scenario that is experienced by this network for a particular fault condition at this point. This is the same network drawn in some other load flow software. So in the case of these constraints, as explained in this previous slide, the renewable sources are curtailed when there are constraints. That means when there are overloads in the network. Why renewable energy sources only are curtailed is that many wind and solar farms are situated far from the demand centers, and since those are far, there might be some weak network conditions or less short circuit power. Because of that, grid lacks capacity to transport power from renewables, and supply demand mismatch, power generation during low demand. When there is low demand in the local network and the generation is more, then the network operator has no other option other than to curtail the generation. And lack of storage at the same time, if there is not much storage, then the excess generation has to go waste. A lack of grid flexibility and system inertia, with the increased penetration of distribution energy resources which are inverter based, there is not much mechanical inertia that is available with synchronous generators. Since the mechanical inertia is not there, there are instability events. Even a small imbalance between generation and consumption leads to frequency deviations. Synchronous generation, yeah, as explained, it doesn't have sufficient inertia. Market and economical factors. If no intense incentives are given to absorb the excess renewables, then there is no. That means the customers cannot involve in welcoming renewable energy sources. Grid code and operational limits, voltage and frequency control, high renewables can cause instability. Curtailment is to be used as a last resort in this case. So, whenever a generator is to be connected to the network, so because of these reinforcement limitations, as they have to use the existing network, the network operator issues a non-firm connection offers to the generators. Means that the generator, if there are no constraints, can export the power, and if there are constraints, it cannot export the power. It has to limit its export. That is the concept of this non-firm connection. Under specified circumstances, a generator can have their export or import restricted or curtailed. That means even that can be curtailed to 0 megawatts. Factors that impact the level of curtailment are location of the network, location of this particular generator on the network, uh, other generators scheduled to connect. If there are many other generators in the surrounding region, those are also sharing the same common existing network, those will compete for the capacity of those constrained assets. So that will be a challenging situation for the other generators, for the other generators that are behind in the queue. Curtailment. So curtailment analysis is to be done to predict how often curtailment will occur for a particular generator, and what is the subsequent impact on that project revenues. So in order to find these curtailment analysis can be done. There are two types of curtailment. One is because of circuit outages, and the second one is because of network management. If there are key circuits that are to be there for the generation to be exported to the wider network, then those circuits go offline. The generators will not have any other choice, any other path to export their power to the wider network. In that case, 100% of this power of this particular project has to be curtailed or to be reduced to zero. That's the meaning of 100% curtailment at that point of time. And coming to network management, the network uh, has that means all the information of the network is communicated to a management system, which is called active network management system, or ANM system. That ANM system uses the data from the SCADA, supervisory control and data acquisition system, SCADA system, and by using the data from the SCADA system, it monitors the status of the network, and if it finds that there are some assets that are getting overloaded because of some generation, then this ENM system sends signals to the associated generators that uh, they have to reduce their generation so that these assets are not overloaded. Different different network management schemes are active network management scheme, ANM, load management scheme, LMS, and within ANM there are transmission ANM and distribution ANM. Uh, Transmission ANM is associated with some transformers which have reverse power flow constraints. We can import the power very well, but coming to exporting power means when there is higher generation in the demand side and that has to be exported to the upstream network, then mm, they will have some constraints, or they will have some limits because of heat generation, or they cannot withstand the reverse uh, power flow. So they will impose some limits on the transformers, that is called TANM. And distribution ANM, the some of the lines may not have sufficient capacity, so that leads to distribution ANM. Load management scheme, this is another kind of network management. It is that means its focus is on the loads instead of generators, but it can intervene the operation of generators as well at times. There are many other names for this network management schemes, such as DAMS, distribution energy resources management system, GEMS, generator energy management system. So all these systems more or less do the same thing, which is to curtail the excess generation of various generation resources. Unfortunately, those are renewable energy sources because those are the latest, that means the recent generators that are added to the network, which are quite behind in the priority queue, because in order to be fair for the senior generators, the junior generators are to be curtailed. That is the policy followed by the network operators. All the recent generators being renewable energy sources impacts the net zero targets. That is what is the challenge for the net zero. Coming to, as we discussed in the previous slide, that curtailment of a particular generator may be because of outages or the network management, because of the network monitoring the various assets. Coming to assets, which leads to 100% curtailment for a particular project. Those outages may be unplanned outages, which are due to faults. If a fault happens, no one can control that fault, that event, and that happens. If there is a unplanned outage, then that leads to 100% curtailment for the project. The curtailment rate or outage rate in percentage is given by outage rate per unit per year multiplied by average downtime divided by hours in a year. It is to be 8760, but considering the leaf year in one of the 5 years, the average is 8766. Planned maintenance. If there are planned maintenance activities of the key assets that are pertaining to a particular distribution energy resource, since that is getting maintained, it cannot export power, and if it is best, it cannot import as well. So, but for that particular duration, the project is to be curtailed. Maintenance of this planned outages are due to maintenance of assets following a typical schedule. Where possible, we use that means it is based on for modeling the impact of this planned maintenance or the curtailment due to these planned outages. We can use historic outage data of various assets and how those are getting maintained over time. That gives us an estimate for the curtailment for a particular project. This is the continued discussion on these curtailment due to outages. Suppose say a generator is getting connected here. It is a renewable energy source, and as it is renewable in nature, its power is to be converted to AC. So there should be a need of inverter and a switch gear. And after that, the generation is normally around 690 volts or zero point 0.7 kilovolts around. It is to be stepped up to 132 kV because this wider network is of voltage level 132 kV. It is to be stepped up to 132 kV. It is that particular voltage to this much of kV transformer. So, and the generator, this constitutes, generator constitutes all these base, solar, wind, followed by inverter, switch gear on the transformer. And this is the wider network. This wider network, as said, it is 132 kV and it has many pylons here. And this is the network. This generator is getting connected to this this part of this wider network. So this is the cable associated with this project. It has a switch gear here and a switch gear here. If there is a fault here, then it cannot export power, so it has to be curtailed. If there is a planned maintenance of this switch gear, this has so in that case also maybe here are the are the switch gear associated with this generator. It has to stop generation. It leads to curtailment. So this can be accounted for in the estimation of curtailment for this project. This is another scenario in which the generator is connected to the circuit that is directly leading to the substation, and the other part of this circuit is getting connected somewhere here. So if there is a maintenance here in the circuit, then it is to be is to be curtailed. Yeah, coming to outages in the generators, those are in parallel. So those are anyway loaded to the n-1 capacity. So those are not accounted for. The failure rates of this, the planned maintenance of these bus bars are very rare, and if those are to be there, those are done along with the maintenance of these transformers. So not additional curtailment is added. This is another scenario in which a generator will be curtailed. Here, generator is directly connected to the generator, so it is constrained by this export cable only. So this is the next section associated with curtailment. Curtailment due to ANM, active network management. Let us go into the details of this ANM. Yeah, here mm, this asset is there. This is the asset of, yeah, this particular. This is the line having a rating of 5 MVA, and there is a generator of 10 MVA and a local demand of 8 MVA. The generator has to supply power to this load, and after that there is an excess power of 2 MVA that can pass through this particular asset of rating 5 MVA. Then this is the most ideal case. Nothing is overloaded here and this passes. However, if the demand of this load reduces to 3 MVA, in this case, there is an excess power of 7 MVA. If that is exported to the upstream network or to the substation, then there will be a problem because this is only rated at 5 MVA, this circuit, and there is an excess power of 2 MVA. So in that case, the active network management system, ANM system, acts in such a way that it sends a command to the generator. It sends a command to the generator, right, to the generator to reduce the power output of this generator to such a value that this asset is not overloaded. In this case, it automatically computes what is the action to be followed by this generator, and it decides that 8 MVA is the most optimal value of generation at this from this generator such that this is not overloaded. So it sends a command signal corresponding to 8 MVA, and it follows that. Then 3 MVA is the local demand, and the rest of the power, which is excess power, is exported to the upstream network. So this leads to a favorable situation for this asset. That is the concept of active network management. It continuously monitors all the assets that are in the distribution network and sends command signals to generators or demand side response systems to adjust their usage or generation. This is another example requiring further insight. Here there are two generators, each of 8 MVA rating. Uh, this is 10 MVA load, and the assets are rated at 5 MVA each. There are two parallel assets, 5 MVA each. In this case, for this snapshot of this uh, generation and demand scenario, there is 16 megawatts of generation and 10 megawatts of demand. Excess generation is 6 MVA. 6 MVA gets shared between these two lines. So each carries 3 MVA each. So it leads to a favorable situation. However, if the demand reduces to 4 MVA, 16 is the generation, 4 is the demand, excess is 12. 12 has to be shared by these two circuits 6 MVA each, which is not good for these assets. So ANM has to reduce their reduce the output of the generators, but it cannot give a signal to the generators so that the generators reduce their output uniformly. The senior generators, which are ahead in the priority queue, are to be given more preference to produce more generation. That means generation as per their rating, and the junior generators are to be curtailed. That is what is the concept of LIFO, last in, first out. If you are connected to the network last, then you are the first person to go out. In the case of any asset violation, if any asset gets overloading, then the junior generator has to go out from the network. That is the concept of this LIFO. So this generator has less preference than this generator one. So because of this, this ANM system doesn't give any signal to here, but gives the signal to here to reduce the output. So that is what is done here, because excess power is 12 MVA, and the allowable capacity is only 10 MVA. It has been given a signal to reduce the output. It is 6 MVA now, and it is now okay. This is an acceptable situation for the DNO, and situation is solved. So in order to compute the energy reduction for a particular project, we need to consider all these things. What is the priority queue? We need to look at the priority queue of the generators and come to a come to a come to a figure for the estimation of curtailment. Yeah, yeah. Let us go to the next one, which is n minus one and n minus two situation. That means there are three assets here, each rated at 12 MVA, and the ANM system acts in such a manner that in the case of outage in any of these lines, then rest of the networks, the rest of the assets should not get overloaded, because each rated at 12 MVA in the steady state before any fault, in which is called the pre-fault scenario. In the pre-fault scenario itself, it adjusts the generation of all the generators such that these assets are not overloaded. In this case, uh, if one of these circuits goes offline, then the available capacity with the others is 12 plus 12, 24 MVA. So all these assets, if all these assets carry 24 MVA together, then there is no problem in the case of one of the in the case of one of the assets fails. That is a pre-event limit set by this ANM. If yeah, this is the case of n minus one, and this is the yeah, in this case of n minus one, the 8 MVA in pre-fault, then all the situation is okay. But if it continues to do so, then in the case of another failure, then one of the assets has to carry the total power, so it has to be 24 MVA, which again overloads this, so which is not good. So it adjusts the limits for these assets to 6 MVA. In that case, ANM system adjusts the generation such that these carry 6 MVA pre-fault, so that if there is a fault, then the assets carry 12 MVA, which is as per the rating of these assets. That is the concept of this n minus 2 scenario of this ANM. Yeah, we now understood that a particular project is curtailed based on the priority queue. If it is lost in the priority queue, it is curtailed first. So all the generation that is ahead of it uh, will not get any reduced generation commands from the ANM, but the generator which is lost in the queue can get if the assets are overloaded. This is the case of a generation. Sorry, this is the case of historical loading of an asset. Positive values are taken as demand values and negative values are generation values, because at times there is little demand in the local distribution network and there is a lot of generation in the local distribution network. So that has to go to the upstream. So in that case, it will be negative here. And this is the rating of the asset minus 50. It is the uh, profile, power profile of a solar plant of 20 megawatts in size. In a sunny day, it will have a peak generation at around 12, 12 p.m. It is just like a Gaussian distribution, but it is as per the solar irradiance levels at different points in time in the day. The hours are 0 to 24, and this loading is also from 0 to 24. This is the power profile of a battery energy storage system. We know that battery energy storage system takes in power at some times, gives out power at some other times. So this is the case of these are the times the battery energy storage takes in power, and these are the times this one are the times at which the BESS sends out the power. This is the case of combined cycle gas turbine. This always is exporting at 5 megawatts. All these generation sources will have an impact expressed in terms of these sensitivity factors on the constrained assets. That means it is not required that uh, a particular generation affects the constrained asset to 100%. Even though 100 megawatts of uh, generation is added at one point, it may affect only 20 megawatts to a constrained asset. That is what is the concept of this sensitivity factor. If it is 100 megawatts of generation affects that constrained assets by a value of 100 megawatts. That is what is the concept of sensitivity factors. So all this generation is to be given a sensitivity factor for that particular asset, which is of 50 megawatts in size. And there are three sensitivity factors associated with these three generators. So these three generators impact this particular 50 megawatts asset in their own style. This is the loading, including the generation profiles. When uh, all these things are superimposed together, this is these are the curves. Along with this, if there is a project, if there is a new project to be connected of 20 megawatts size, consider the case of sensitivity factor of 1 here for simplicity. In this case, it clearly exceeds this limit of this 50 megawatts for this particular asset. In this case, uh, all this, all this generation in excess of this 50 megawatts is to be curtailed. So the generator will lose this much of revenue. The revenue associated with this much of time and this much of power is lost by that generator, which is not good for the generator in terms of revenue, and which is not good for the country as far as net zero targets are concerned. Because if the renewable generation is curtailed, the demand is to be met through other fossil fuel sources. So it doesn't add to net zero and the impact. In fact, it worsens the situation. So these are the challenges for the generators. And in order to model this further, that means in order to analyze this curtailment problem deep, we need to find what the constraints are, what are the constraints for each of these projects that is given by the network operator to the customer or the generator to be connected. In terms of that means those are given in offer documents when a generator is given an offer by the network operator. mm, the point of connection or location of this generator on the network is given. Network schematic is given, that is available through long-term development statement of each of these DNOs. We can look at that, and after that we will see all the assets that are relevant to this particular project. Here the project is connected here. This is the GSP means, um, which is 275 or 400 kV divided by 132 kV transformers are there here in the GSP. um, and after that this is grid supply point GSP. And after that, there are some lines that lead to the BSP as well. BSP means bulk supply point or grid. And from grid, we and that means there is a line that is leading to primary, and in between this, on this line, this project is connected. So, in order to understand the curtailment faced by this project, we need to get the information from AFO documents regarding the project location, and the surrounding network is identified from this LTDS. And after that, the loadings of all these assets, these transformers, these lines, and this line can be constrained to the generator. So information regarding the loading of these lines or assets is to be obtained, that is given by DNO, which is distribution network operator. After that, these asset capacities can be found out, even that is there in this LTDS, long-term development statement of each of these distribution network operator. DNO specific methodology, how the DNO operates the active network management scheme. Is it based on 95% derating of any asset? That means if 95% of the rating of any asset is reached, generators are given signals such that they have to reduce their generation. Is it based on N-1 or N-2 outages, etc.? So all this information is given in this DNO specific methodology. There are other constraints such as reverse power flow constraints, directional overcurrent limit constraints, etc. Those are to be understood. Suppose say there are 3 transformers here, each of rating 200, 200, and 350. One of them has 350. In order to represent the worst case scenario for these transformers, that means the worst case capacity that is available with this GSP is to consider the case of a loss of the highest rated transformer. In that case, it will face the worst case scenario. So this GSP is now left with 400 MVA rating multiplied by this derating factor. This derating factor is generally applied by GSPs or DNOs uh, because uh, because it is 400 multiplied by 0.95 means 380. When the power flows through these transformers reach 380, then the ANM becomes alert and sends signals to the generating resources. Otherwise, if it waits till 400 MVA limit, then meanwhile the generators may increase their power further, not knowing the constraints, and these assets can get overloaded in the meantime. That is why there is a derating factor of some value that is used by the network operators. Means during the time the ANM sends the signal to the generator and the generator reduces the demand. It may take some seconds to minutes of time. During that time, there should not be any risk of overloading the assets. That is the concept behind this derating factor. There are two dual circuit overhead lines, each of rating 70/70. So, in order to consider the worst case scenario, um, only 70 MVA rating is is to be followed by this ANM, and it is associated with a derating factor of 95% as well, or 0.95. Coming to this TNOHL, TN means it is like a T, right? T that is not looped in, looped out. Looped in, looped out connections are generally given for the demand connections, which require security of supply. If one of the lines, if this section goes offline, the supply can be restored through the other way. But that is not required for generators because security of supply is not that much of a concern for generators. Because we are considering TNB to reduce the cost of the cable that is going to the project. That is the concept behind this TN. So since this project is teed in, this this is directly applied derating factor, and as there is no other line, so all these things are to be taken into consideration in the assessment of this curtailment for this project. And as discussed, some projects are given this non-film non-farm generation connection offers means export of power from those generators is not guaranteed. That is based on the status of constraints. If there are some constraints, then they have to adjust their generation such that there is no violation of those constraints. That is what is the concept of non-farm offers. Those are associated with the last in first out stack or priority stack as discussed before. This is provided by DNO or inferred from embedded capacity register, which is followed by each of these DNOs. So there is the overloading, that means historical loading is there. If the projects are connected in the LIFO stack, if the projects are connected before the historical loading data we got, then there is no need for the projects to be added to the assessment. For each of these GSP or grid supply point, we need to look at all the projects that are getting connected, to ignore all the projects connected before historical loading data. And rest of the projects can be sorted based on the date accepted. That gives us an indication of this priority stack. And after getting that priority stack, we can find the LIFO stack for this for a particular project. This is to know whether a substation is teed in or not. If that is based on the distance from the substation and capacity. If the POC voltage point of connection, POC means point of connection. Here it is 11 kV. If the capacity is less than 3 megawatts, then definitely that is to be teed in. If it is 33 kV, then if it is if the distance from the substation is greater than 5 km or capacity is greater than 20 megawatts, then it is to be teed in. That kind of rules are there that needs to be understood. And this is a typical case of mm, sensitivity factors that are associated with each of the generators on the constrained assets. There are three projects here: generation 1, generator 2, generator 3, and on the top of all these three, there is this project as well. On the top of means in the list of these generators, and this generator is the most junior generator out of all these three, so it is to be least preferred. That is what is the concept. Coming to a generator, mm, so coming to the GSPs at this SGT means super grid transformers. Those are there at this grid supply points. There are three SGTs, one, two, three, and they will get a that means um, here generator one is there. Um, its generation is shared by these three transformers equally. Means one divided by three, that is 0.333. 0.333 for this SG2, SGT2, SGT3 has this 0.333 again. Coming to generator 2, it is the same concept. Its generation, which is here, if it is exporting, then it is shared among these three equally. So that is true for all the generators. Coming to dual circuit OHL, if we consider generator G1, there need not be any sensitivity factor associated with this, because this generation from this G1 is no way concerned with these assets. If it is exporting, it goes through these SGTs and doesn't need to pass through these assets, OHL assets. So this generator G1 has sensitivity factor of 0 and 0 for these assets. However, for these G2 and G3, if there is an export that is to be shared by these two equally, so zero point 0.5, zero point 0.5, and this is G3 and 0.5, zero point 0.5 for G3 as well. Coming to our project that is situated here, this has to um, share. That means this export has to be shared by uh, these OHLs. So minus zero point 0.5, minus zero point 0.5 here. T in, yeah, coming to T in, G1 and G2 don't have to do anything with this asset. Only G3 and our project are to deal with this. So they have a sensitivity factor of -1, -1. That is the way of understanding this. So this way, we can do the curtailment analysis, and if the situation is quite complex, and if all the network is quite meshed. Here in the previous slide, we discussed about a simple network. This is radial in nature. We don't need to model this in a complex power system software, such as Dick Silent Power Factory or ETAP, that kind of softwares. If the situation is complex, like there are many GSPs that are getting connected to um, the distribution network, then we need to we cannot manually do the sensitivity vector computation. So we need to approach some Dixieland modeling software or similar software. Coming to, that is, so far that is what curtailment is and how it is practiced in by ANMs. Coming to the solutions to reduce curtailment, what we can do is we can expand the grid, or we can do some reinforcement to the grid so that transmission capacity is increased, and we don't need to curtail the renewable energy generation, which is good for both generators as well as the nature. Energy storage integration. If we use batteries or pumped hydro, the excess energy that is generated from the renewable energy sources can be fed to the storage so that it need not be wasted. Demand response and flexible loads. Yeah, as discussed before, if we use demand response, if the generation is more and the customers are consuming at the time of that excess generation, then there is no need of the curtailment, and it is natural that since the generation is more and demand is less, it is natural that the energy prices are also can be reduced at that point of time. If that kind of incentives are given to the customers for using the demand, for using the power at the times of excess generation, then customers are definitely encouraged, and they can the adopt the practice of demand side response. Interconnectors and cross-border trading, export excess energy. If there is an export energy, you don't need to curtail and just export through interconnectors or cross-border trading. And hybrid systems, advanced grid management system, all these schemes can be integrated so that we don't need to curtail the generation. So the last but one slide here, future energy scenarios. So there are different scenarios for future energy. It is possible with the engagement of all the stakeholders in the transition to net zero by uh, as soon as possible. So that can be done by electrified heating, consumers willing to change behavior, means they use high energy uh, apparatus or equipment. They use demand side flexibility, fastest credible decarbonization. When all these things are practiced, and if the transport is also made electric by with the adaptation of electric vehicles, then one can, or any country can reach net zero by their target years. That is mm, that is the concept behind this. Uh, Coming to the role of electric vehicles, they can also contribute to reduction in the curtailment, shifting the demand away from the peak periods. If there is peak demand period, electric vehicles don't need to get charged in that duration, and they can just shift their demand away from the peak period so that there are no assets that are constrained. Utilizing excess renewable energy generation. When the ANM system sends signals to these electric vehicles to utilize the excess renewable energy generation at the times of the excess generation, then they can utilize that, and that is good for the generation sources, nature, as well as the EVs themselves, because at the time the energy prices can be made lower so that those are quite affordable, alleviating local grid congestion. So they can help in alleviating local grid congestion, providing grid balancing services. The generation has to be equal to the demand. That is the concept behind this electricity system operator. That is the very duty. That means the significant duty to be followed by any system operator. So for that, if electric vehicles also do their part satisfactorily, that is quite good for the network, because grid the imbalance leads to instability. Differing costly grid reinforcements with the increased demand side response and these excess renewable energy utilization. You don't need to reinforce the grid. You can just defer the investment on the reinforcement. Supporting vehicle to grid technology. So the electric vehicle is connected to the grid, and it gets charged and discharged as per the grid requirements. That is the vehicle to grid technology. So all these things can be followed by electric vehicles, and it is good for the curtailment. That means reduced curtailment is achieved for generators. It is very much good for everyone, customers, countries, nature, everything uh, becomes quite beneficial with the increased use of electric vehicles for transportation. Yeah, that is this session, and I thank you everyone uh, for patiently listening to this session, and I welcome any questions.
Any questions from the participants? Please interact. If you have any questions, you can feel free to ask. Any questions? Okay, sir. I think there are no questions.
Oh.
We conclude the session one. So thank you, Dr. Vidyasagar sir, for accepting our invitation to be a part of this Atal FDP program. And thank you for providing informative session and insights into the curtailment in power management system. And thank you once again, sir. Thank you very much for joining.
Yeah,
Thank
I thank everyone attending this session, and I thank the organizers as well for giving this opportunity to interact you on this very good topic of curtailment. Thanks again, once again.
Thank you, Sagar. Thank you.
Thank you. Bye.
Okay, participants, we will resume the session two very shortly, and we will have a break for 10 minutes, and then we will resume the session two shortly. Thank you.
Sir, good evening, sir.
Good evening. Can you hear me?
Yes, yes. Sir, can we start in 5 minutes?
Yeah, sure.
Good evening, sir.
Good evening, sir. Vinit, sir.
Good
I
evening.
am
Dilip.
Dilip. Good evening, sir. So, welcome to our AICT Atal FDP program. I wholeheartedly welcome you, sir, on behalf of Department of Electrical and Electronics Engineering, Sri Vishnu Engineering College for Women, Bhimavaram. And I'm very happy, sir. Thank you for accepting our invitation to be a part of this our FDP program. And we are looking forward for your session. Before your session, I request Dr. M.V. Srikanth to introduce today's speaker. M.V. Srikanth, sir, please.
Yes, sir. Good evening, sir. So I would like to give a brief introduction about today's speaker. Dr. Vineet Vajpayee is an accomplished engineer and researcher with over 14 years of expertise in system modeling, control systems, and signal processing. He currently serves as a senior engineer modeling and simulation in control and instrumentation at Rolls-Royce SMR Limited, where he leads the development of C&I design capabilities and supports advanced control algorithms and simulation initiatives. Concurrently, he is a visiting researcher at University of Sheffield, focusing on system modeling and control design for turbine engines. Dr. Vajpayee holds a PhD in engineering sciences from Homi Bhabha National Institute, Mumbai. He earned a master's degree in instrumentation and signal processing from IIT Roorkee. Throughout his career, Dr. Vajpayee has contributed to advanced projects, which has led to numerous high-impact publications on robust control, fault detection, and multi-scale modeling. Thank you, sir. Thank you for accepting our invitation. I request you to start the session.
Thank you very much for the introduction, and thank you very much for having me. I'll share my presentation. To keep it interrupted, I'll turn off my video while delivering the presentation. I'll put the video on when I finish the presentation.
Okay, sir.
So can you see the presentation in a full screen mode?
Yes, sir.
Yes, sir. Thank you very much. Thank you, Srikanth and Dr. Dilip, for the introduction. Today's topic of presentation is on the AI application in nuclear power plants in smart grid systems. The brief outline of this task start with the introduction, defining what exactly is a traditional grid and what is a smart grid. We would be looking more into the nuclear energy mix, and in general, we would be looking into the consumption and what sort of projections are there. We would be focusing more on the nuclear side as well. Then we would be moving towards the artificial intelligence, where artificial intelligence come in, how it can help us in delivering more power from our plants, how it can help us in delivering a better grid. We would be looking into the recent trends and challenges. We would be also looking into where artificial intelligence is applied in an ongoing plants and where it can be applied in a near future. And in the end, we would be looking into the opportunities and the future direction. We would also be focusing a bit on the challenges that are there. I'll try to keep the presentation as interesting as possible. I hope not to bore you out. In case of a traditional grid systems, it generally refers to a conventional electric grid that operates in an unidirectional manner. So for example, the grid is transferring the electricity to the consumer. And so it's basically in a flow directions. It is having its own problems. For example, with the introduction of so many renewable energy sources, introduction of so many consumers who are now also as a producer, the demand fluctuation that are happening over time because of different energy sources, and the aging infrastructure. These challenges help us, and actually they are helping us in the direction of moving towards smart grid. So what exactly is a smart grid? Is a digitally enabled electric grid to improve the efficiency, reliability, sustainability of electricity services. So it basically collects and works on the information about the behavior of all the suppliers that are there and consumers to better manage the energy delivery and transmissions. As a smart grid, it mainly comprises of three elements. So a smart control and measuring device, followed by a two-way digital communication system and a computer software program. As you can see in the infographic, that a smart grid is able to integrate the starting from smart houses to the electric vehicles, as well as small scale energy production, as well as large scale energy production. If we are looking more into the benefits of smart grid, why exactly we need it, the main reason behind the optimized operation of the system, it helps us with enabling demand response and demand side management. So for example, if there is a new entrant coming into the system, how we can manage that, how we can allow them to come and provide the services to end customers as well as the new customers. It would also help us in case of the bulk generation of energy. So for example, if we are able to generate more energy, for example, in a traditional nuclear power plants, they mainly work as a base load operation. But if we want to generate more energy where we can store it as we get more renewable sources in the mix, in the end, it will also help us in case of retail customers because they have a high level of knowledge. The customers are, like I said, producers these days, and the customer is always looking for a best deal. They are trying to go to the system where they can get best value for their money. A large number of microgrids that are also coming, like off-grid communities, the demand responses. So to understand how consumers are usually, for example, in countries like Europe, the demand and consumption of electricity is very much during winter months of around, like for example, Christmas, and in January, whereas in other months the demand slows down. To do an analysis on this demand response and as well as to the transmission and distribution. It would also help us in reducing the environmental impact, optimizing and the efficient use of all the available assets that are there. In the end, it would also help us in improving the reliability and the security of supply. So what exactly is the current energy landscape? How exactly it is looking? If we look at the global energy consumption trend in 2022 or 2025, for example, in terms of British thermal unit, we can easily see that where we are and where we will be going, countries like the United States, Brazil, South Korea, and Canada, they are almost linear and not increasing. They would be staying constant as compared to what would be their next 25-year consumption, where when you look at countries like India and China, they are going to ramp it up. For example, in case of India, the current consumption is somewhere sitting around 45 British thermal unit, and it can go to 3 times around 120 British thermal unit. Whereas in case of China, you can see it's going to enhance in the next 5 to 10 years, and then it's going to stay constant. So what is the reason behind these trends? Where are the resources coming from? How are we going to use all these resources? And to understand more on this thing, we need to have a look at what are the various contributors for the energy sources. If we start like 25 years back around 2000, and then we look at the current scenario and moving towards the next 25 years, we can steadily see that the consumption of oil has remained constant over the last 25 years, and more or so it will decrease slightly because of the natural resources that occurs in nature. Whereas if we look at other sources such as natural gas, the consumption has increased. For instance, the consumption of renewable energy, hydroelectricity, nuclear has increased. And if we look at the next 25 years, you can clearly see in terms of a percentage where we are at 617 exajoules, and we would be going to 635 exajoules. And this extra energy is actually coming from the renewable and the nuclear side. Nuclear it's still on the lower side in that, but if we look into all the renewable energy sources that are available there, we can easily see that it's going to bring us a challenge there. It's going to help us in achieving the clean energy sources. So what exactly is the role of a nuclear power? And nuclear power is a critical component of global energy production. It's as we all know, it's one of the cleanest source of energy. It helps us in reducing carbon emission. If I just give you a data, so for example, the CO2 that is released per kilowatt hour of energy produced, we can see that a coal plant releases around 1,000 grams of CO2, whereas a natural gas produces 500 grams of CO2. If we look into solar, which stays at around 50 grams, and for hydro, it stays at 25 grams, whereas for wind and nuclear, it comes down to only 10 grams of the CO2 that is produced or released in the environment. So in terms of a coal plant, we can see the nuclear is able to reduce that energy emission by 99%. If we look at the data, that who is producing what sort of energy, as of 2020, if we look at the data, 31% of the total electricity that's produced by the nuclear in the United States, followed by France and China sitting around 13%, whereas India, if you can see at the bottom left, it's around 2%. So we are only able to produce 2%. We also need to understand which countries are actually making more on the nuclear. So for example, France is almost producing 70% of its net energy through nuclear, making it one of the cleanest energy producers country in the world, followed by Ukraine at 55% and other countries over there. As of the global trend that is sitting over there, in 2020, like I said, at 2,500 terawatt hours of global energy production were there. If we look in the previous graph, we still see that it's not a significant amount, but when you look at the number, 25,000 terawatt hour, it's not a small feat. Now, which countries are going to produce more, or where people are going to put their resources and money? We also need to understand what is the outlook of nuclear energy in India. So as of September 2023, according to International Atomic Energy Agency, it reported that around 410 nuclear power reactors are in operation in 32 countries around the world, and 57 nuclear power reactors are under construction. So where exactly India sits in that table? In terms of the countries with most nuclear reactors, we can see the United States as of 2022, the United States sitting at 92 reactors, whereas India sitting at the 6th position, 19. They got 3 more reactors. So as of current 2025, we are talking about India got around 25 reactors. You can also see one more thing when you look at the changes that has happened since 2011. You can see that China has already put a lot of resources on this, and they have drastically increased their reactor capacity from 13 to 55 by putting 42 reactors. India is slightly behind. We were able to put only 2 or 3 reactors in the last 10 years, but the outlook is where we are looking in the future. In terms of the renewable energy capacity, that in 2023, according to the sources by the Ministry of Power and Central Electric Authority, India was producing almost around 400 gigawatt of electricity, out of which half of the electricity was produced by the coal and half of it was produced by the other sources of energy. You can clearly see nuclear sitting around 7 gigawatt, or as of now, it is around 8 gigawatt. Whereas renewables, if I combine nuclear with that renewable energy group, you can see renewables are happily contributing around less than half of it. So who's going to do more in this thing? So the question is, who's building more nuclear reactors? In terms of the gigawatt capacity, you can see China, again, in terms of the capacity, is around 60 gigawatt they are producing with the help of the nuclear reactor, and they are going to double it up and going to take it to 120 gigawatt. In case of United States, they are not ramping up that much. They are already producing more than 100 gigawatt through the nuclear, whereas France, which is producing almost 60%, 70% of its electricity through nuclear, is producing 64 gigawatt. When we look at India is producing 8 gigawatt, but in the near future, if you look at the other number, which is sitting next to the 8, is the 32 gigawatt. So India is going to quadrupling its capacity. So if I try to rearrange this figure, seeing who would be producing more capacity in terms of where they are, in terms of the percentage there, because absolute cannot give us a right figure. Sometimes you would say India would be sitting at the top. China was sitting at the top, and China already have ramped it up, and that's why it's just doubling the capacity. And if you remember the graph that we have looked at the consumption, in the next few years, China is going to increase its power consumption, then it's going to stay constant. The reason is they have already put in all the sources that are there, and that's why. Whereas in case of India, it's just increasing 3 times, and that's why we are producing almost 4 times of nuclear energy in the next few years. So where exactly the role of AI comes in all this nuclear energy and other sorts of energy? Now, as we have seen, artificial intelligence is impacting every facets of the life, starting from how we arrange. For example, the meeting that we are having as of now is through Teams instead of having a traditional one-to-one or one-to-many presentation. It's Bitcoin, all sorts of things that are there, the mining and stock markets. If we look at bulk energy production as well as small scale energy production, the smartphones that we use and the electric vehicles, smart grid, how we're going to use all those things. So artificial intelligence is affecting all the facets of life. The definition of artificial intelligence is kind of like artificial intelligence. I would say it's an umbrella term which comprises of different sources such as machine learning, neural network, deep learning, generative AI, and human at the center of the AI as well. So to summarize this thing, we can say artificial intelligence is a machine-based system that can, for a given set of defined objectives, can make predictions, recommendations, and decision influencing real and virtual environments. Artificial intelligence systems use machine as well as human-based inputs to perceive real and virtual environments, abstract such as perception into models through analysis in an automated manner, and use model inference to formulate options for information and action. In short, we know the artificial intelligence can be a machine learning or can be a neural network, such as a multi-language perception, can be as simple as a principal component analysis or support vector machines, or can be some trees based on random trees or decision trees. It can also be recurring deep learning methods such as recurring neural network, or for example, large language models, natural language processing, all these sort of things. So from in this presentation, whenever I'm going to use the word AI, I'm actually referring to one of these techniques which fall under this term, whether it's ANN or machine learning. So what is the role of artificial intelligence in energy? By providing a concise framework that complements and extends existing methodology, the idea of artificial intelligence is whatever we already have, can we use them in a better way? Can we use them for the optimization purposes? So artificial intelligence in the energy sector start from the planning. So for example, one of the topic which is you might have received a lot of attention in the last 5 days of this faculty development program is on the electric vehicles. So the idea of electric vehicles is how we can plan them, what is the right route for them, where the resources need to be put. We don't want to put the resources, for example, in a marketplace which is already a busy place and so many people just coming over there and they are not able to utilize it. Whereas, for example, if you put some resources in a remote village where again not many people are utilizing those things, we are not able to utilize those bits. So the idea is how we can put these electric vehicle charging point, for example, how we can route these things so that we can have these resources available throughout the place, and then people can buy more electric vehicles. I mean, this is one of the concern in the case of electric vehicles, is the infrastructure is not there. How we can have that sort of infrastructure in its place, and when the electric vehicles come into the picture, it's going to be a more dynamic system. So there, because we don't know how many consumers are going to charge their vehicles. So again, artificial intelligence can help us, giving us some data about the habits of the people, what time of the day people are going more to the work. So for example, during 9 to 5, more people are going to the work, so there's a less consumption of electric vehicles during this time, but more consumption before going to the work or after going to the work. So the artificial intelligence can really help us in planning all these things. It can further help us in multiple battery usage, how we can efficiently use it. For example, if I have a Tesla car and I want to drive it, I want to take it to next point so that I would be able to reach to my destination without worrying about whether I will find an electric charging point or not. That might influence my decision in buying, whether I want to buy an electric vehicle or whether I want to stay with the traditional petrol and diesel engines vehicle. Eventually, artificial intelligence is going to affect a lot on the electric vehicle industry, which will ultimately affect the smart grid systems. On the other side, in the energy sector, is on the robotics. In case of robotics, it can help us, for example, in case of detecting fault in a line. So a fault can occur on a different line, and it might take for a person to go there and figure it out where the fault is there, for example. But instead of doing that, if we can utilize other techniques such as the UAVs that are there, and we can assemble those UAVs and then use those UAVs to figure it out where exactly the fault is in the line, and based on that generated data, we can update our models, we can train the models, and we can use these models to predict that next time onwards that there is going to be a fault and what type of fault it is going to be. These are the things artificial intelligence can help us. Another thing is about the solar cell production. It can always help in the production of these things, how to efficiently plan the production and how to efficiently execute it. In case of machine learning, it can help us, for example, in failure prediction. It can also help us in the better management of the electric grid based on the demand and supply. And as we got more renewable energy sources in the mix, so how we can utilize them in the best way, in the best optimized way. The last but not the least is in the computer vision technique. And it can help us in, for example, in solar potential geomapping. It can help us with the proactive geospatial monitoring and defect classification. For example, if it's an oil pipeline or if it's like a component, we want to know if there's a fault in that component before we go into a large scale production. A large pipeline, it's very difficult for a person to go there and figure it out, all those problems. But if we can have automated data monitoring sensors, these sensors can give us information on a timely basis, and we can, based on this timely basis, we can generate some models, and these models would be able to help us that what type of fault it is. If they can help us with fault categorization, and once we have found the fault, we would put the right resources and time to sort out those faults. So the role of artificial intelligence in smart grid. In case of smart grid, need artificial intelligence for example, real-time energy distribution and demand forecasting. Artificial intelligence will help us in ensuring stability while mitigating threats such as cyber threats, which is a crucial concern for nuclear integrated grid. It will help us in case of, for example, the adaptive energy demand forecasting, sorting out the problem of grid instability enhancement and the load balancing. On the management side, it would help us in reducing the outage. For example, even if we get a grid which is working at 99% of its power, and let's say if there is a downtime of 1%, it will make us sit in the dark for a few days in a month, which we can't tolerate. So we need a system which is working more than 99% of its efficiency. And to do this thing, and with the emergence of all the smart grids and the integrated AI, it can literally significantly enhance the efficiency, the security and reliability, for example, in real-time grid optimization using different algorithms. Not but the least, the cybersecurity for smart grid would again be a main concern, as more and more sources are there, and the unsocial element, they want to target those things. As we all know, these days the wars, they are not in physical, they are happening in cyber, where they are affecting people on the cybersecurity place. So artificial intelligence can literally be a game changer in this case. And in the end, it's about the renewable integration with nuclear power plants. As we all know, with the nuclear power plants, they are one of, we need to keep them safe, and because of the radiation and other threats that are involved, and they can become a potential source for attack. And in that case, affecting a nuclear power plant. So how are we going to sort out these problems? Using the artificial intelligence and machine learning. Before moving into the conversation in the artificial intelligence in nuclear power plants, I would like to give a brief overview what exactly is a nuclear power plant, so we all understand what could be their potential benefits and what could be the potential applications. So on your screen, what you're seeing is a typical animation of a pressurized water type reactor. The difference between a conventional thermal power plant station and a nuclear power plant is how we are converting that in electric energy. So in case of a nuclear power plant, the conversion to electric energy that takes place indirectly, whereas in a conventional thermal power plant, that happens on a directly. So how exactly all these things work? So it all starts in the reactor vessel that you're seeing here. A tiny particle called a neutron that smashes into an atom, causing it to splitting it, and a chain reaction from there onwards happen. And if the chain reaction is maintained, then more and more neutrons are released. We call this process fission. And the fission in a nuclear reactor, what exactly it does, it's like what you are seeing, the red lines that are moving, the water is circulated, which is also called as a coolant. And on the other side is again water. So you can think in a layman term, it's basically water to water energy transfer. So the fission that happens in a nuclear reactor, it heats the reactor coolant, which is circulating around in the reactor vessel. That coolant can be water or gas or even liquid metal. For example, in a pressurized water reactor, that is the plain water that we have, the seawater. So it depends on the type of the reactor. The reactor coolant then passes to the steam generator. But now you can see there are two different colors of water. or the reason behind this separation is because we know the water coming from the reactor vessel can be radioactive. So instead of directly using that water, we have another water, which is like, you can say, the secondary coolant, which is also water. What the secondary coolant is doing is able to take the heat out from the primary coolant, and you can see what is happening in the steam generator. The bubbles are forming. So the reactor coolant then goes into the steam generator and heats the water to produce the steam. Once the steam is produced, the pressurized stream is usually fed to a multi-stage turbine, steam turbine. So you've got high pressure turbine, low pressure turbine, intermediate pressure turbine. And these steam turbines, what they try to do, they try to expand and partially condense the steam. The remaining vapor is finally condensed using the condenser, and you can see it's again fed back to the steam generator. So what exactly is happening here? The condenser can be a heat exchanger, which is connected to a secondary site such as a river or cooling tower. The water is then pumped back into the steam generator and the cycle begins. Now you can see on the generator side, from here, whatever heat sources we are able to transfer that heat into electricity, which is connected to the grid and can help us in supplying the nuclear energy to the public. So that's what the basic idea with a nuclear power plant. A nuclear power plant, you can say it's a thermal power station with the heat source is your reactor, the nuclear reactor. In terms of fuel, so for example, in a thermal power plant, we have coal. In case of nuclear power plant, we have something called enriched uranium. So the uranium that is found in nature, we'll try to enrich it, try to make it fissile, and then use that enriched uranium as a fuel. The coolant can be, like I said, it can be water, or depending on the type, there can be different types of reactors. So for example, this one is a pressurized water reactor because the water is pressurized. Another one is a boiling water reactor in which we allow the water to boil. So very much the name says what their type of things they are. And that's the idea with our nuclear power plant. So what exactly is the benefit of artificial intelligence in nuclear power plant? How it can help us, artificial intelligence in nuclear power plants? So the three main potential benefits in case of nuclear power plant, which we all can think of, is, for example, and they might be applicable in all the plants, but in case of nuclear, there's more concern on safety and security. The safety and security, the first one, is not only about the plant, it's also about the reliability of what is called structure, system, and component. In short, it is abbreviated as SSC. So it's the reliability of the structure, the systems, and then the component. The structure can be your containment structure, the concrete building, and the components can be your valves, pipes, those sort of things. It is also dependent on the reliability of the humans, because humans are the operators that are there. So we need to know that they are able to benefit from this application of artificial intelligence. It can help us in, for example, accidental radiological release and monitoring. So if, for instance, let's say if there is an accidental release that has happened, instead of vacating all the people from the nearby area, artificial intelligence can help us. For example, there are models that are available looking into what is the wind direction, what is the amount of release, which part of the population is going to get more affected, and which part of the environment is going to get more affected, so that those people can be shifted to a better place if there is some unforeseen situation happens. And artificial intelligence can help us in solving these big issues in a better way. The third thing is about the cyber security and the physical security. So artificial intelligence, for example, as more and more components are connected, the digitalization of our nuclear power plants is happening instead of analog components. These digital components can be affected through, for example, a digital software or through some virus. So artificial intelligence can help us. It can help us in identifying the patterns which are usually unnoticed by humans. And they might be, we haven't thought about those strategies beforehand. The artificial intelligence can help us in designing some strategies for those cases. Moving towards the second bit, which is about the plant analysis. So in case of plant analysis, artificial intelligence or machine learning or these advanced model can help us, for example, with degradation modeling. They would help us in figuring out how to model the faults, the cracks that are happening there, what would be their future impact. So for example, if there's a crack happening up, when it's going to become a significant, when I need to go and change. For example, if more and more components are getting affected, when should I go and start changing things? This would help. Artificial intelligence can help us in those directions. Another thing is about fault detection, diagnosis, and prognosis. It can help us, for example, in identifying faults in the sensors and in the actuators. So, for example, in case of nuclear power plants, we got two types of sensor: one which sits inside the core, one which sits outside the core. If I have to change the components which sits inside the core, I need to stop the plant, then I need to wait for some time so that the reactor is shut down. It's not like a thermal power plant where once the plant is shut down, I can go and access it. In case of nuclear power plants, we need to wait until it's shut down, the reactivity is below its level, then one can go and replace. So in case of nuclear power plants, these procedures where we have to change the components and shutting out the plant, they are not cheap one. They cost a significant amount of money to the companies, to the public, because ultimately it's the electric company needs to make some money by selling out that electricity. If they are putting too much money in production, then that energy is going to come at a cost. The last thing is about plant O&M, which is the operation and maintenance of the plant. Not only of the plant, is of the structure, systems, and component, and helping us in delivering better efficiency. So for example, having the control rod drive mechanism that are there, it can help us with their optimization. It can help, for example, instead of an operator sitting and lowering the rod to decrease the power or taking them out to increase the power, we can make these operations as autonomous. And once these operations are autonomous, they can help us in delivering better power. It will also help us, for example, in operator performance evaluation. We can see whether those operators who are sitting there, are they too tired? So that, for example, if they are too tired, they might miss some things that are happening. If we look at the previous accidents that has happened, most of the accidents, one of the major concern is about human error. So how we can reduce that human error? Artificial intelligence can help us in understanding their behavior. It can help us in how to rotate those human operators in a better way, so that they, instead of doing those labor intensive tasks, they are more focused and they are able to make better judgment. And the last one is about on the maintenance and planning. So again, it will help us in, for example, in how to better plan things. Like I said, a maintenance of a plant is again a big issue, because at that time the plant is going through a downtime, and when a plant is going through a downtime, you are not able to produce any electricity. And again, in case of nuclear reactor, neither you can start it by a snap of the finger, nor you can stop it. It takes time. So we need to understand all these things, and if we can have a better planning. So for example, some of the fuels in a nuclear power plant, we need to constantly rotate it around so that we can see that we are able to burn the fuel in a uniform way. And these maintenance issues or maintenance activities that are there, they need to be planned in a better way. Again, when we talk about reducing load on humans, if humans are going and looking into this maintenance task on a daily basis, they might miss few things. For example, there is a large amount of nuclear data which is available. If we can utilize that sort of data in understanding how to better plan the maintenance, we can always sort out these problems. And these three main issues that are there, they would help us in enhancing the safety. They would help us in reducing the human cost and labor cost, which ultimately will help us in producing cheap electricity. And if the electricity is cheap, the government can put more and more money behind renewable or nuclear. And again, it will help us in safety evaluation and improvement, because again, in case of nuclear reactor, safety is of paramount importance. We need to evaluate it on a constant basis, as we also need to improve it, which ultimately help us in, for example, producing better accident mitigation technology, evaluating the scope, and removing the source of failure. So to summarize these bits, one, like I said, on the safety and security assessment, enabling the data collection and analysis at larger scope and faster speed, increasing the design process efficiency. So for example, we are able to design better reactors which can perform better. One of the concern in case of nuclear reactor is the amount of energy that is produced, and as compared to the electricity that is produced, the efficiency sits at around 33%. So you can see there's like 66% of energy that is produced. We are not able to convert that into electricity. So if we can have a better design, if we can have better procedure so that we can transfer this sort of energy into electricity, we can literally change the game. Suggesting improved control strategy, for example, as I talked about the control or drive mechanism, and optimizing resources allocation, automating labor intensive work, and streamlining scheduling and maintenance. So in case of nuclear power plants, what are the major places where we can, the artificial intelligence can literally help us at? Artificial intelligence can definitely help other plants, whether it's thermal or other renewable energy. But in case of nuclear, artificial intelligence is going to make a big difference because of the problems or the challenges that are there in case of a nuclear power plant. So the first one is about simulators and digital twins. We are going to talk about these topics in detail. Some of the topics I'm going to talk about it. I'm just going to list all those things that can be potential and where it has already made some changes. Simulators and digital twins. We have already heard this another umbrella term, digital twins. And another thing is about autonomous control and real-time optimization. So instead of having manual control, now we see a lot of controllers that are there. You already work and familiar with a lot of advanced controller, whether it's adaptive control. Can we use those controllers, or example, robust control techniques, or techniques such as sliding mode, or adaptive controls such as L1 adaptive control? These advanced control algorithms that are available in the theoretical domain that have been used in other sectors, can it be used in a nuclear environment to deliver better performance, and so that we can also have a real-time optimization of the sources? Reactor monitoring and diagnostic. Again, one of the main challenge with a plant is to monitor on a constant basis, looking into the data all the time to make sure that we are not missing out any useful information, and we use it for our diagnostic purposes. Predictive maintenance and failure prediction. Again, in this term, it's all about prediction. We don't want our system to fail, because in case of nuclear reactor, we call it a fail to, we design it to such as a fail to safe system. So even if it fails, it remains safe. Now, how we can use these philosophies using the artificial intelligence in case of nuclear power plant, how we can predict the maintenance, where we want to maintain what would be the downtime, instead of making my plant to go downtime during winters when there is a lot of demand of electricity. We can make it during summer months when there's not a lot of demand of electricity in cold countries. The next one is about the fault detection and anomaly prediction. So for example, predicting if there's an anomaly in a sensor, or if it is in an actuator, or if that anomaly is happening in a process, or for example, a component is there. Fuel cycle optimization and management. This is one of the important thing, where it's like a lot of research and development goes into the fuel cycle. So if artificial intelligence can be used there, and it can help us in a better optimization and management. For example, techniques such as reduction of waste, how to transfer that waste which is produced, which is usually a big concern in a nuclear power plant. And if we can use artificial intelligence over there, we can always use the resources in the other part. For example, development of new novel fuel elements. And the last one is about safety and emergency response systems. So for example, like I said, if there's an accidental release of radioactivity in the environment, how we can use techniques. There's already techniques such as Kalman filter, unscented Kalman filters, particle filters have been used to design, to tell the regulatory agencies that this would be the approach that one has to follow if there is an accidental release of radioactivity, looking into the wind, looking into the data, looking into demand. This would help us in putting all those emergency response in place. If we have better and better emergency response in place, it would provide the safety net for the public. This would also help us in gaining more confidence in a nuclear sector from the public. Now we will be looking a little bit onto these application in detail. So for example, looking into the simulator. So what exactly is a simulator? So this is one of the picture of which is a Russian VVER full scope simulator. So you can say a simulator is kind of like, it can help us in simulate the process. It can be an education purpose, such as a PC based simulator, or it can be used for training purposes such as engineering simulator or full scope simulator. So the purpose of a simulator can start from testing instrumentation and control, then training the personnel, for example, for computer aided engineering. It can also help, for example, in operating shift training, how to do the shift training. It can also help us in case of maintenance training and assessing the emergency response and behavior. Ultimately, we want to reduce that human error. So in case of human factor engineering, simulator is very useful as compared to a normal PC-based simulator, which is used for teaching students and pupils knowing about how a nuclear power plant works and assessing their response. They can play around, they try to understand them, different components that are there. The engineering and full scope simulator, they can be used for training purposes, and like the nuclear, or in case of all nuclear power plant simulator, there are some few elements are going to be common. For example, you can see in the pictures, the instructor station is there and a power supply to run the simulator. There are going to be cameras which might be recording your behavior as well. Try to understand how you are responding to some scenario. For example, I can give you a trip scenario that the reactor is tripped and how you can save that reactor from tripping, or how you can respond in that scenario. That would help us. The next thing is about the cables and servers. So you can store that information, transfer the information across the plant, and control room replicas. So instead of a nuclear power plant operator or a control room operator sits in a control room a bit away from the nuclear power plant, and from that control room, they control the whole power plant. So this control room is kind of a replica. The simulator can be a replica of the control room, and it will assess how you're going to respond in scenario. For example, you can have a lot of training, how you're going to work on it, but some situations might be there where you don't know how to respond in this case. The simulator can help us in assessing those scenarios. Full scope, if I talk about a full scope simulator is actually capable to recreate any physical process and logical function of a reference plant in a real time, or in slow time, or even fast time. So you can say the full scope simulator is actually my virtual plant, especially from a nuclear instrumentation and control perspective. Another useful importance of and the benefit and the application of artificial intelligence is on system modeling and control. So what exactly is a system modeling and control? So system modeling and control, the nuclear power plant that we have seen, it can help us in designing and modeling, writing physical equations, physics-based equation, or data-driven equations for core modeling or for thermal hydraulic analysis, how the transfer of heat is happening, how there's the energy balance equations are happening. On the right hand side, what you are seeing is a screenshot of a PC based simulator supplied by International Atomic Energy Agency, IAEA. It's called PCTRAN. You can see that, I don't know whether you are able to read it, but in this case, this is the front HMI that you are seeing. On the back of it, all the mathematical equations are written, and on these equations you can literally work with this system and try to understand if you want to change your control design, if you want to change your another models, the way you are modeling it. For example, in case of steam generator, how you want to model it, if you want to model one steam generator or two steam generator. So artificial intelligence can help us in this case, because with the help of artificial intelligence and machine learning, we can do what is called reduced order modeling. So instead of having very complex models, what we can do is, like, we can come up with simpler models, first order or second order models, because as we know, as a control system engineer, my controller is going to be as complex as the model itself. So instead of having a higher order model, I can always work at a simple model and always design simple controller strategy to control a complex process. Design of advanced reactor control algorithms. So for example, now we see a modern reactors such as small modular reactor, micro reactors, space reactors. They are in the research and development stage. I mean, if you look at the US and other places, they got the nuclear reactor, which was installed around 1970s. The design hasn't changed much. In other countries as well, people are working on towards the new design. So can we utilize artificial intelligence or machine learning or neural network in the design of advanced reactor control algorithms, as I mentioned? Adaptive control system for real-time operational adjustment as well. So for example, not only just designing, if a scenario has happened, if we are going to connect these nuclear power plants to the grid, in that case, what would happen? The nuclear power plant should be able to demonstrate load following capabilities and other capabilities as well. When we talk about the load following capabilities, that if, for example, let's say if there are 3 systems connected to grid, if one system fails, the nuclear system and the other system, they need to ramp up their production. So can we use for adaptive control in a real-time operational adjustment? Or for example, if there's some fault or outlier in the data that has happened, can we adjust if the supply said from the grid, the grid operator said we need to reduce the power of the production by 10%? Can the system do all these real-time adjustment? And again, it's not just doing those adjustments. Can we do it in a better and an efficient way? These are always the questions. And here, the last but not the least is using artificial intelligence for risk assessment and safety modeling. So if there's a risk scenario, for example, like we talked about the leakage and the containment structure, if these sort of scenarios are there, how we can use the artificial intelligence in modeling those scenarios. One of the main thing that we are hearing is a digital twin. A digital twin, you can think like it's similar to a full scope simulator, but it's more like it get more characteristics. So a simulator can be used for a different plant. In case of a nuclear digital twin, it has to have these 4 characteristics, I would say. These 4 characteristics, the first one could be, it needs to serve a nuclear purpose because it's built for nuclear. A digital twin has to exist in a digital form. So on your screen, you can see on the left-hand side is the nuclear power plant, where all the information is existing in the form of a physical asset of physics phenomena. The sensor instrumentation is physical. You got the wires, the cables, the pipes, and all those sort of things. You also got human working and operating the plant. On the right hand side of that graph, you see a digital twin. So the idea with digital twin is it has to exist in a digital form. It has to maintain that state concurrence. What is meant by state concurrence? For example, whatever the state of the plant, it's like the digital twin should be able to show the same thing. So you can think like this thing: we have a nuclear power plant running, and a digital twin is doing the same thing in a digital manner. So ultimately, the digital twinning is telling us what is going on in the plant. So instead of we going on figuring out on the plant, on a digital twin, we can do this thing. It would help us in putting a lot of data, in gathering a lot of information. The digital twin can enhance our several capabilities. So for example, because it's running in a digital mode, there is a lot of digital information. It can help us in communicating that information with other plant operators. It can also help us in communicating that information with the grid, that we might suspect something might be a case and we might need to go through a downtime. It can also help us in analyzing what is happening with a better integration, and in the end, we can control the scenarios. The last characteristic of a digital twin is it has to ensure a state cognizance. By what I mean by state cognizance is it should be able to, so whatever information we are giving to the new digital twin, it should be able to produce that particular state in a plant. So for example, because everything, it's not a physical one, the digital twin is a digital one. If I supply it with a given state and given initial condition, it should be able to tell me what would be the state of that plant, which will allow us to run different scenarios. We can run the plant through different cases and we can see whether my system is working correctly or not. One of the main thing in case of digital twin is on the data and information management, how you store the data. You can always see that whenever we are talking about the data, there are again going to be challenges coming into your mind. Is my data secure? How to keep my data safe? How to share it in a better way? How other people can corrupt my data? Because again, it's a digital plant. They can, if somebody puts a virus in your system and your digital twin is not working correctly, you might think that your plant is not working correctly and you might end up taking a bad decision. So these are the challenges that are there. On the modeling and simulations type, again, you need to have better data analytics, better machine learning techniques available there, because a lot of data is going to be produced. And once that data is there, you should be able to generate a lot of models, whether they are generative language models or whether they are just fault detection and isolation based model or physical mathematical models. These models should be data informed as well. So they should tell us whatever is happening in that data and how we can use that data and the model for the better and the safety and the security of the plant. So to summarize these things, a digital twin is, like I said, a virtual representation of a nuclear energy system. It uses the real-time information and other data resources to improve the process. It helps us. Actually, this is one of the major point, which is about the design, licensing, construction, security. So licensing and regulation in itself is a long and lengthy process. With the digital twin, if we are able to supply all that of information to the regulator would have a better confidence in judging the design. They might ask better questions, and instead of asking and the same question in different way, we might be able to answer the question and with supporting with the data as well. It would also help us in decommissioning and waste disposal. So for example, what should be the strategy that we need to adopt and when we should decommission it based on the current state, because once we have the digital information, we can always use for prediction, and we can always use those predictions and we can make those predictions as accurate as possible based on data training. And once we have that sort of information, we can use this digital twin for better judgment. The next thing that we look is into the reactor system design and analysis. So the model development that we are talking about can be based on a structural experimental data or numerical data generated by simulation codes or simulators. Artificial intelligence, deep learning, SVM, Bayesian neural networks, fuzzy methods, kernel methods, all these methods can be used in the design of advanced reactors. So as of now, you see most of the places, they have this large conventional reactor, which is around, according to IAEA, 700 megawatt electric. Now we are moving towards what's called small modular reactor and micro reactors. Different countries are putting a lot of money behind these small modular reactors because of the advantage they bring in. They are modular, kind of like a factory built thing, like you have a modular kitchen at your home. Yeah, these are the modular reactors, which are 80% are built in the factory. They would be taken, whether it's taken over a lorry or a barn, and then they can be taken to the site. They can be assembled over there. And once they are assembled, they are ready to produce the power. So with this advanced system design and analysis that is happening, artificial intelligence can help us, for example, with the data analysis, to learn from whatever experience that is available in case of large nuclear reactor. For example, Westinghouse is producing a new small modular reactor based on the advanced design that they already have for large conventional reactor. In India, AP300, AHWR 300, they are planning to build, which is based on AHWR 100,000. Again, replicating the design, trying to rescale the things, and use the experience and the knowledge and the expertise that is available in case of large plant to deploy in case of small and micro reactors. In case of design of thermal hydraulics, reactor system physics, because again, when we talk about scaling something on a bigger scale or scaling it down, we need to, the equations might remain same, but there has to be some other challenges coming up. With the use of artificial intelligence, we can address these questions, we can answer these questions. We would have better confidence in whatever we are generating. So we won't be like a cowboy who is just going to go and work. We are using the previous data that is available and using that available data and knowledge in building the state-of-the-art techniques. It can also help us in models and code uncertainty analysis. And for example, component simulation using different simulations code. So we can, the different simulations codes that are available, they can be used to doing simulation on a component level. The simulation can be done on a micro level, or it can be done on a dynamic level. So instead of doing things on, for example, in case of fuel, doing thing on a pallet level, if I'm a control engineer and I'm just interested in the dynamics of the plant, I would like to look at a more macro level. So that sort of analysis can be done with the help of the tools that are available. Plant operation and maintenance. So in case of a nuclear power plant, the operation phase of a nuclear power plant is generally the longest phase of its life cycle. So there are performance indicators are used for monitoring and assessing the performance of operating nuclear power plants in a qualified manner. Detection and diagnosis techniques for detection and isolation techniques based on principal component analysis, partial least square, mean squared error, those sort of techniques that are already available. Different sort of data, whether it's performance data, weather data, baseline model, can always be trained based on these data, and a model can be fit, and then accordingly we can always diagnose those faults, and then we try to sort the problems. In case of operation and management, the autonomous management and control to mitigate the system plant anomalies and the accidents that are happening, starting from the diagnosis, going towards the prognosis. Advanced techniques such as load following operation can be implemented, which would be really helpful in case of grid, smart core controller, alarm processing system, system-based diagnosis. These are the scopes where the technique can be used, and the technique can be used to enhance the efficiency of the system in terms of the operational and maintenance. The last one would be the cybersecurity solution. As you can say, we are digitalizing our nuclear power plants. We need to have a better security in place, especially looking into the cyber side, so that we can have dynamic security, risk management, technical evaluation. So instead of, because cyber risk can be a dynamic threat, we might not have seen that sort of virus previously, and one has to address the problem on a real-time basis. In case of nuclear fuel materials, which is again one of the costliest thing in case of a nuclear power plant, it can help. Most of the 80% of the research and development happens on determining the fuel performance. And the fuel performance, believe me, it involves complex fabrication logistics, long irradiation qualification campaigns, and the performance analysis for accidental tolerance and post-irradiation durability. With the help of artificial intelligence, what we can do is we can accelerate these things on determining the fuel performance, and when we can utilize the already available nuclear data that is available, and instead of doing this thing, we can redirect our resources towards determining the fuel composition. So for example, which may help us in figuring out novel fuel types with unique capability and safety and efficiency characteristics, which can be inherently stable. We would be able to reduce time. It would also help us in case of material selection for waste reduction. Again, instead of figuring out what should be the best material which is going to produce the least amount of waste, because the nuclear waste can be a concern. One has to put all the things in the place, how they are going to deal with the waste that is going to be generated after nuclear power plant has gone into its decommissioning. Those things can be sorted out with the help of the data that is available. Focus can be on the investigation of fuel composition and fuel factors, which might help us with the novel nuclear fuel types. Moving towards the nuclear safety side, which might be the last not the last slide, might be the last application that we are talking about. On the safety, we need to have, it is of paramount importance to develop emergency preparedness and response plans as a measure of abundant caution. And these plans need to be tested and regularly revised. Artificial intelligence can help us in supporting these regulatory decision making, in which one has to prepare all these plans. Radiological emergencies at NPPs are broadly classified into plant, on-site, off-site, emergency based on area upon the situation. Now, nuclear artificial intelligence or the data analysis can help us in dividing and classifying these things and prepare better answer for on-site, off-site responses. The reviewal and approval of these emergency preparedness and response plans for both plants and on-site, artificial intelligence can give us a better answer. This can help us in analysis of the structured data and the test data and the free text data. Beside these emergency preparedness aspects are checked during routinely regulatory inspections. So it would help us in reducing the burden on the routine regulatory inspection, and those inspections the resources can be redirected towards the other side. So from the nuclear safety, on the safeguards, as well as on the security. So moving towards the later half of the presentation is where exactly these AI tools are working in the ongoing NPP, or is it all happening on research and development stage? So yes, most of the things in case of artificial intelligence in nuclear power plant is happening in a research and development stage. The reason behind it, because one has to have all the regulatory procedure in its place. One has to address a lot of questions that are there. And there's a sudden boom that is happening in artificial intelligence. The nuclear industry don't want to be left behind. They want to utilize the time to put all the resources. So Blue Wave AI Labs, which is one of the company, it has produced some tools, which is like predicting the moisture carryover in case of a boiling water reactor, or predicting the eigenvalue evaluation in case of a boiling water reactor. Core design, which can help nuclear physicists in designing their core in a better way. For example, placing with help us the placement of fuel, with the placement of sensors, with the placement of actuators. It can help us those things. Flux mapping system, which kind of like looks into the current state of the nuclear and different components that are there, how those components are behaving and what sort of flux is producing. This will help us in figuring out where we are producing more flux and where we are producing less flux. The idea with this thing is it can help us in making better judgment, better analysis, and better technique. Westinghouse has recently revealed its nuclear generative AI system called Hive. Westinghouse is already using in multiple regression-based AI and machine learning. They have already put the resources there. EDF is defined a company called Metroscope, which has, EDF is a French company, which is French nuclear company with looking into the root cause analysis. There are some things are at the development stage. So the XE100, which is a digital twin being developed by the X Energy, it's at the development stage. Other than these customized solutions, there are some off-the-shelf solutions that are available, such as IBM Watson's. These tools have been used, and they have been used for quite some time in the nuclear industry. Now, we have talked a lot about the advantages and the disadvantages, and we have also talked about the benefit and what could be the potential. AI also introduced the technical, cybersecurity, and regulatory challenges. Nuclear power plants are designed and constructed, commissioned, and operated in conformity with the stringent safety requirements, which ensure adequate margin for safety. But with the advent of this AI, what could be a possibility? The data accuracy, we need to ensure it, the data security and data reliability. Wherever there's data involved, we need to make sure that it is accurate. It is not giving us some false positive, and then we might end up believing that thing and taking an action. Next thing is about the algorithmic transparency and interpretability. The algorithm might be able to give it an answer, but we need to understand in a better way how things are happening. Is it transparent enough, or is it something which we can't understand? Because we can't understand it properly, then we can't implement it. For example, then who would be liable for that particular thing if something goes wrong? And do we interpret the things in the right way, or is it like my interpretation is wrong? Another thing is about high data processing demands and AI model accuracy. So with artificial intelligence, the demand is going to be more and more. How are we going to sort out these demands? System reliability and transparency in AI-driven decision making. Again, it's all about we are having a human and AI interaction. So who is going to be responsible for that? If something goes wrong, is it the human or is it the AI? Because we can't put the blame on the AI, because it's just a process developed by the human for the benefit of human. We need to use and address these questions in a better way before adopting and fully indulging into this thing. Next thing is the integration with legacy nuclear systems. So the old power plants that are in operation, which are using analog systems, which are using previously developed techniques, how we are going to integrate this thing with the new technique, how we're going to integrate all these things in a better way. That is again going to pose some serious technical questions. In terms of regulatory and ethical and legal concerns over AI decision-making in nuclear operation, they also have to be addressed. So for example, complex nuclear regulatory process such as waste management activities for radioactive waste, which generated, and licensing of significantly AI-enabled plants, I would say, and other nuclear fuel cycle facilities. What would be the AI role in this, doing this critical thinking and critical decision making, how it's going to compliance with the nuclear safety that is already in place? For example, in case of nuclear, we have like principles of defense in depth, redundancy, and diversity. They are inbuilt in the design, and it is ensured in every activity. Once we have the AI autonomy in this case, would also need to be addressed. Ethical concern, like I said about, and the accountability and legal framework for AI decision making. Who is going to be accountable if things go wrong? And what are the legal frameworks? We can't bring a computer in a court and we can't say that this computer has done something wrong, right? So we need to have all these questions addressed before implementing these things. The last one is about the cybersecurity risk. What are the cybersecurity risks? So the nuclear cyber attacks. surface is increasingly getting complex. Why? Because of globalization and decentralized manufacturing. So instead of manufacturing coming from one place, again in India, more private sector people are going to come into the nuclear side. So manufacturing and supply of these nuclear reactor components is getting decentralized. There are some vendor-specific vulnerabilities. These vendor-specific vulnerability could be inherited by modern plants with digital control and instrumentation. And these inherited vulnerabilities make it difficult to propose a one size which is going to fit everyone in a nuclear cybersecurity environment. There's a problem with threat detection and intrusion prevention. How are we going to figure it out if somebody has corrupted my system or somebody has accessed my system? Because previously the nuclear power plant, they don't used to connect to the internet. That was one way, but now with the digital twin and AI, that is going to change. Once they would be connected, they would be there would be chances of having these attacks. Assessing the vulnerabilities in nuclear digital assets is a complex task due to the need for configuration of specific assignment that consider interconnected devices, connection types, different protocols. So one has to develop all these strategies for these AI-driven security announcement and the risk mitigation strategies. Moving towards the end of the presentation is what are the opportunities and future direction? AI offers immense potential, from improving reactor design to optimizing markets. So for example, advanced reactor design such as fusion reactors. As AI continue to evolve, we can expect safer, more efficient nuclear power system. For example, with having autonomous control for next generation reactors. This would help us. Nuclear technology companies are actively integrating AI into advanced reactor systems, such as trying to use that thing to enhance their design. Collaborative research is also expanding in AI's role in nuclear operation. So improving regulatory compliance automation. Because of this collaborative research, can we do it automated way? Because this is the place where it takes a lot of time. And resilience against climate-induced disruptions. This is again one of a future direction. The research and development of hybrid AI models combining rule-based approach and machine learning. And this is one of the key areas where a lot of companies are putting their efforts and money as of now in case of a nuclear reactor. We have talked a lot about how we are going to use artificial intelligence for nuclear power plant. But we haven't thought about, when we talked about producing all these sort of models for artificial intelligence, the ChatGPT or GPT-5, these sort of models that are available in the market, they need a lot of training data. And where we are going to store that data? So the question is about data center. How are we going to power that AI? The solution might be in nuclear. It's like a win-win situation. So the data centers that are there, they can be powered through nuclear. Recently, companies such as Google and Microsoft, they have put a lot of money behind nuclear power plants, and this is happening in the last 6 months. The artificial intelligence is definitely going to help the nuclear side, but the nuclear is also going to help the artificial intelligence. So this might be a win-win situation for both, for the artificial intelligence and for the nuclear power plants. With this thing, I would like to say thank you very much.
Thank you, sir. I request participants, if you have any questions, you can please interact with the resource person.
If you have any question, please feel free to ask. You can also email me later on if you want. Yes, please. Someone got his hand up. Ravi Teja.
Any questions from the participants? Yes, sir. I think there are no questions. It is Indian time. It is already 9. I think people are very hungry, and so yeah. Thank you, sir. Vineet Vajpayee, sir. On behalf of Vishnu College, I wholeheartedly thank you for accepting our invitation and to be a part of this Atal FDP program. And we look forward to once again in future. Thank you so much, sir. Thank you very much for your
Thank you very much
nice,
for having me.
informative session. Very informative session. You have given all the insights into AI and smart grid nuclear reactors aspects, and it was a nice, very nice session. Thank you. Thank you so much, Andy.
Thank you very much. Thank you, everyone. You're being a nice audience. Have a good evening. Thank you. Bye.
Thank you. Bye.